Second speaker is Fred Lerdahl. Fred is Fritz Reiner Professor of Composition at Columbia University. His 1983 book, Generative Theory of Tonal Music, co-authored with linguist Ray Jackanoff, broke new ground in proposing a rigorous theoretical framework for the study of music cognition, and it's become one of the most widely cited books in music research. His second book, Tonal Pitch Space, building on the theoretical framework of the first book, has also been widely influential. Fred is also an accomplished composer, winner of the Kusevitsky Composition Prize and numerous other prizes and commissions. Please welcome Fred Lerdahl.
Thank you. It's an honor to be part of this wonderful occasion and celebrating these three very important authors. And thank you to everybody for making this happen. The title of my talk is correct, but if you look in your booklet, you'll see that there's a different abstract. I think what happened was that I changed the title and changed the topic and forgot to send Steve my new abstract. So if you want to read about another paper that I'm not giving, you can read the abstract. I want to begin by a little bit of thanks. Of course, people know that I wrote this book with Ray Jackanoff, and I was able to do things in music theory and cognition that with him that I would never have been able to do on my own. But it's equally true with Carol Krumhansl, although I authored the book Tonal Pitch Space myself. It was the whole idea of the book came from her work that was codified in the Cognitive Foundations of Musical Pitch. But the original work came out from the early 1980s, and it was a real eureka moment for me to read that, of the kind that David Huron had earlier with Al Bregman, because it showed me the way to how to make parts of my theory work to bring it to a level of sophistication and computational precision that I had not been able to do before. So I got to know Carol a little bit after, I suppose in about 1984 approximately, and I often consulted with her while I was writing Tonal Pitch Space, and she was extremely helpful in helping me realize my ideas. Then later on, that book was published in 2001, and then after that, Carol and I decided to collaborate on testing an important component of the tonal pitch space theory, the tonal tension model. And it took us quite a while to work this out. It was a very big study published in Music Perception in 2007. So I had the opportunity to work with her directly, and she's so intelligent and such a great experimentalist. I always felt I was in good hands, and maybe most of all, in terms of collaboration, she really takes the trouble to understand music theory, and she has the musical understanding to be able to really understand music theory. So it was a very close and productive collaboration, and I'm very grateful for it. Now on to my talk today. The original GTTM project was to take the musical surface of a piece of music. One would like to start with the audio signal, but that was too difficult, so Jackanoff and I began with the musical surface, basically a piano roll representation. But when a listener hears a piece of music, the listener doesn't just hear a musical surface, but hears all kinds of structure, and that gives the music meaning and understanding, and its many aspects of its expressive qualities. So our idea was to build a rule system that would take the surface and predict the structural description or the heard structure. I can convey some of Carol's influence on me by referring to components of this theory work. What you have in the blue boxes are the hierarchical components of GTTM. On the lower left are the stability conditions, and that was part of the theory that was very under-theorized. So when I wrote Tonal Pitch Space, I built Tonal Pitch Space on top of GTTM and expanded its scope in a number of ways. But the most important thing for the moment is that the pitch space component, which is in the same spot as stability conditions, there. Now, all the red ones are components that were a part of tonal pitch space. But the pitch space thing it came out of modeling the empirical work that Carol and people she worked with developed in the 1980s. And all these other components are part of the TPS model. And if the green ones are parts that came directly or indirectly out of her work. So that's my summary. Now, my talk today is about concepts and representations of musical hierarchies. What I'm going to report on today is part of a larger sort of comparative study that I haven't actually completely finished. I want to go through various components and talk about the notation, the representations, what they say, what they don't say, where the problems may be, and so forth. When I talk about musical groups, it's a little bit different than in auditory scene analysis. Jackendoff and I assumed that music was one stream. There was a sort of a simplification of our theory. But when you hear even one stream, you're hearing units of music. You're hearing motives within phrases, phrases within sections, and sections within a piece, and so forth. So you can notate groups in any number of ways. Groups are, I should say, musical groups in this sense rely very heavily on Gestalt features, some of the same ones as in auditory stream segregation. So there's a real relationship between the two approaches. So you know, if an event is within a group, then it's within a bracket or some other similar notation, and then groups are grouped within larger groups. So this is uncontroversial. But if we go to metrical structure, there have been a number of different kinds of notation for metrical structure, and some of them say different things, which have theoretical consequences. When I was a kid, I learned that the hierarchy of a 4/4 measure was as in case A, where a capital S stands for strong, small s stands for less strong, and W stands for weak. And so the hierarchy of the 4/4 measures, first beat is strongest, the third beat is intermediate, and the second and fourth beats are weak. Now that's a true statement, but the notation doesn't explain anything about the hierarchy. The same is true of the foot analysis that was taken into music theory, actually going back centuries, but goes back ultimately to Greek and Roman prosody. But it's the same thing. They describe, but they don't explain. Longet-Higgins adopted the notation, a tree notation in case C, so that the third beat branches off of the first beat higher up than the second and fourth beats. So there's kind of leveled hierarchy there. So the second beat actually belongs to the first beat. The fourth beat actually belongs to the third beat. So in this sense, it's a constituent hierarchy. The trouble is that depending on the musical situation, the fourth beat, for example, might be an upbeat to the following downbeat and not an afterbeat to the third beat. So this notation is somewhat problematic from that point of view. If looking at case D, you can take the fourth beat in the first measure, and I can take the tree and make it branch to the following strong beat. Longet-Higgins didn't do that, but it's certainly possible to do that within a theory of meter. So these kinds of operations were happening also in linguistic theory around the same time, and linguistic theory introduced metrical grids right around the same time that Jackendoff and I did, and that's in case E. So the metrical grid doesn't have a constituency. That is, the second or the fourth beats don't belong to the adjacent strong beats, one or the other. Same with the third beat to the two down beats shown in the figure. Rather, each beat, each level, there's a level of beats. Each level has equidistant beats, at least in this example. And if a beat is strong at one level, it's felt to be a beat at the next level. So therefore, you get 2 dots for beats 1, 3, and 1, and then finally beat 1 receives 3 dots because it's the strongest level. So that shows the periodicity involved in metrical perception, but it doesn't show constituency. So this is the notation that Jackendoff and I adopted. One could also take a wave notation. One finds this in Zuckerkandel's work from the 1950s or 60s. It's a little more awkward, but it can translate into the dot notation. So far, the moral of this little story is that the choice of notation not only illustrates a structure, but also entails theoretical claims about it. This theme will continue as I move now to pitch event hierarchies. I'm not going to go through this list of historical precedents for pitch events hierarchies, but I made it up, and so I'll just proceed and go right to Schenker. So if you take case A in this slide, this is the first figure in Der freie Satz, which Schenker's magnum opus, published in 1935, where you have a 3-2-1 Urlinie, or fundamental line, and a Bassbrechung of 1-5-1. So this is the Ursatz, or fundamental structure. But actually, the notation doesn't show the hierarchy. It shows the structure, but here it's undifferentiated. If you read on in Der freie Satz, you soon find out that the actual hierarchy is as in case B. And here it's shown by a hierarchy of levels. So at the second level, in case B, the dominant chord is eliminated. And then at the end, the tonic chord with the tonic and the melody wins out. This hierarchy can also be shown using just slurs and note values, as in case C. Here, the slur shows that the dominant chord is subordinate within two tonic chords, and it shows that the second tonic chord is superordinate to the first one because it's a half note rather than a quarter note in value. So there, the note values indicate not duration but structural importance. One can use a tree notation for these relationships instead. In this case, the dominant chord has to belong to either the first tonic or the second one. So in case D, that's what it shows, whereas in case E, the dominant chord belongs to the second one. I'll have more to say about belongingness in a short while. Constituent hierarchies can be represented by slurs and note values instead of tree structures. So that's in case F. Here the case F corresponds to case D, and case G corresponds to case E. Finally, one could use in the final case, H, you can use a tree structure and a slur notation if you want to just duplicate it, and it's something that I often have done in my theoretical work. In GTTM, we did an interpretation on these tree structures so that right branching signifies tension, a motion toward tension, and left branching signifies a relaxing motion. These can combine into very complex tree structures. In case C, it's just four chords where we have a tensing process, then a relaxing one, and the last one in this analysis shows that the last chord is subordinate to the first one. The tree notation has an advantage that it specifies hierarchy very precisely at all levels. And nevertheless, there have been criticisms of the tree notation, some of which I take more seriously than others, but I will review them briefly here. The first one is that this notation is unfamiliar and difficult to use, especially in complicated cases. I take this criticism seriously, so I often, where possible, I use slurs and note values because they're you're reading more normal musical notation or a combination thereof. The second criticism is that the tree notation is insufficiently horizontal in the representation of event structures. More precisely, it does not show separate streams in the Bregman sense. That's true, and that was a simplification of the original theory. But I show in tonal pitch space that, at least in tonal music, the deviations of streams is fairly local, and the hierarchy builds up into larger levels, everything aligns so that you can actually use a tree notation. So what I do in tonal pitch space is I use slurs at local levels and the tree for larger levels where the streams have come together. There are kinds of music, including, for that matter, much music that I myself have written, where this wouldn't be possible. But in the case of tonal music, it is. Another criticism is maybe the most interesting one, which is that it is felt by many people that a subordinate event, such as a neighboring or passing event, may not be subordinate to a single superordinate event. That is, it may not exactly belong to one or the other. You may have felt that with that progression that I had a moment ago. Jackendorf and I debated about this issue, and we thought about complexifying our notation to accommodate cases like that, but then we would have had to have a decision process for deciding it, and the actual notations of analyses would have been very difficult. So we finessed it, figuring that we could always find some reason that would tip the balance in favor of a right or left branch. However, in tonal pitch space, I got into using double branching, as in this case here, where here we have a passing note. Now it can belong to one or the other, so I can branch it either way. And in this case, when I use a dashed branch, it means it's somewhat less important as a connection. I can show this in a more complicated case, in case B here, where here I'm doing a tension calculation to anticipate my discussion. So I have a progression, a harmonic progression, and the two-chord in first inversion can branch either way. So I have both branches going. However, one of the basic principles of tonal pitch space is that you always take the shortest path. Elaine Chu referred to something very similar in her talk a few moments ago. And so if you take the shortest path, you're calculating the distance and also calculating the tension relationships, either getting more tense or more relaxed, depending on how the branching goes. And so it turns out that the intermediate event with the double branch in this progression is slightly, the distance is slightly smaller if it's the left branching pattern. So that receives the solid branch, and the dashed branch goes to the one that's slightly longer in distance. So there's a principled reason or principled methodology for determining these double branchings in the theory. A final criticism of the tree notation down at the bottom of this figure is that it's claimed that it's unrealistic to assign a complete tree to all the events in a piece. I agree. But this is not a criticism about tree structures. This is a criticism about hierarchical theories that, like Schenker's or GTTM for that matter, that assign hierarchies at all levels. But the point about this, from my point of view anyhow, is that GTTM is a final state rather than a processing theory. And indeed, most music theories, including Schenker's, is a final state theory. I think processing is incredibly important. Jackendorf's and my strategy was that if you have a final state theory, then you know what the structures are and the principles by which they're organized by listeners, and then you're in a much better position to develop a processing theory. So I think developing a processing theory is really important, and if one did it, one would find that nobody hears complete trees except in very short examples, and there's probably a lot of difference among listeners depending on the situation musically. The issue of large hierarchies is compounded because it's very difficult to find a good way to test these intuitions, and these, even though it's had a long tradition within music theory. The issue is further complicated by the fact that certain authors have conflated closure with tonic prolongation. So, closure is when you feel both tonally and rhythmically and so forth that we're coming to a close. Tonic prolongation is when you're coming back to the same tonic, or maybe you've modulated and gone to another tonic. So these are not the same things, and one can find examples in the literature or construct examples quite easily where you have good closure and you don't have tonic prolongation. So I think that the studies that mix these two up are compromised in that way. Then there's the foil method, where you substitute an event at different levels of the hierarchy to see what its effect is. That's achieved some somewhat promising results, but it creates other complications that one doesn't want. I think the best evidence for event hierarchies that I know of is actually what I did with Carol in our article, Modeling Tonal Tension. The way it works is that we're able to, through the tonal pitch space model, we're able to measure the degree of tension from one event to a next, either sequentially or hierarchically. If it's done sequentially, it's just from one event to the next. If it's done hierarchically, you compute the tension down the tree structure. So they come to you get a very different set of numbers. Then if you test people on the same piece of music or musical passage, and they're recording their tension, and then you have the theoretical predictions, and you see how well they correlate. If you take the sequential predictions, they don't work at all. But if you do the hierarchical ones, they work really quite remarkably well. And this is true for a number of different listeners, different kinds of listeners. So at least on this evidence, this is a strong indirect evidence that listeners are hearing hierarchically, because otherwise the tension model doesn't work. Then very recently there was a publication by Stefan Kulsch and Martin Rohrmeyer and collaborators adducing brain evidence through electrical responses in the brain that using in a few Bach chorales, phrases from Bach chorales, that people are hearing hierarchically. This is exciting because it brings the discussion from a behavioral to a neural level of description. The evidence from the Lerdahl Krumhansl paper and from the Kelsch et al. Paper challenges views that downplay hierarchical structures in favor of flat schematic patterns, statistical learning, or non-hierarchical mathematical modeling. This is not to say that these other approaches aren't important, but it's a challenge to them to account for these findings about hierarchical structure. The same evidence undermines the hypothesis that only the language capacity possesses hierarchical syntax. This was claimed in a famous paper by Hauser, Chomsky, and Fitch about a little over 10 years ago. Music has hierarchical syntax as well as language. Finally, I need to say that in the Kelsch article, they incorrectly state that Carol and I, quote, did not provide evidence for processing long-distance dependencies. In fact, we provide a good deal of evidence, much more than they do, in fact, but at a behavioral level, using much longer examples and a much greater variety of examples. And we discuss it at length in our paper. So I need to make that correction. I want to move now from event hierarchies to tonal hierarchies, which has to do more immediately, more centrally with Carol's work. The tonal hierarchy represents schematic knowledge of pitch, chord, and key relationships, and it's the input to creating an event hierarchy in my tonal pitch space model. So I'm going to be really quick about this. Some of you, I'm sure, are familiar with this, but I'll just run through this because I want to get back to something else. This is the basic space of the tonal pitch space model. It represents something that you all know, which is that at the bottom of you have the chromatic pitches. The diatonic pitches come out of the chromatic level. A triad is built out of notes of the scale. The triad itself has an internal hierarchy with the third less important than the fifth, and the fifth less important than the root of the chord. This corresponds to the psychoacoustics. So this representation of a C major chord in C major gives you a hierarchy of any pitch that's important at one level becomes that's relatively important at one level is a pitch at the next level, and so forth, just as in metrical structure. This can, if you take the most important representation of each pitch in the basic space, you see that it looks very much like the C major key profile in the Krumhansl-Kessler article. So it's a kind of formalization of it, you could say. It can also be represented by numbers, and if you represent it by numbers, here I'm using Fort numbers from set theory and music theory. And if you represent them by numbers, then you can do numerical algebraic operations that then will allow you to calculate the distance of any chord in any key to any chord in the same or a different key, and come out with a simple calculation that corresponds to the empirical data. This can also be done with the binary notation, and in fact, the computer implementation of the model is done with binary notation. There's a rule which I'm not going to go into much, but there is a rule that's quite simple that accomplishes all these results. And here I'm representing a dominant, going from a tonic chord in C major to a dominant chord in C major in the first example, and the second one, a tonic chord in C major to a tonic chord in C minor. But I could give any of them, and it would spit out, it would give the representation and spit out the numbers. So you have all these sets of distances of chords and tonics from the tonic of one key to the tonic of another key and so forth. And you can represent these things spatially, basically kind of spatial mapping. And if you get this, you get a cycle of fifths on the vertical axis, and on the horizontal axis you get, in this case in chordal space, a diatonic thirds cycle. And this is a kind of two-dimensional array. If you pick something like the 7 chord and to realize that they're all the same thing, then you can turn this into a 4-dimensional structure without repetition. Here's the chordal core, which I often use in my representations. I have models for non-diatonic spaces too, but I'm just discussing the diatonic one today. Here's the representation of regional space on the left, which corresponds with a little twisting to the Krumhansl-Kessler key space. It's a little bit more regular, but basically it gives the same information. So here you have the cycle of fifths on the vertical axes and the parallel and relative minor keys in relation to a major key surrounding any major key. And this continues again, and it would receive a toroidal solution if mapped geometrically. But all of these are just representations. They all go back to the algorithm that predicts the distances, which is really very close to the key profiles. One can also combine the chordal representation and the regional representation into one, where in this case, if you take C major right in the middle, here the C stands for not only for C major, but for the tonic of C major. And so around it is the chordal core in each case. And one can then, if you map going a pitch-based journey as you are listening to a piece of music. Now I'm going to, from this brief introduction of the relationship of the pitch space, okay, I'll be fast. This is Martin Rohrmeyer's analysis of the beginning of the Bach chorale, or Munterdicht. Rohrmeyer's model was used in the Kelch study, which is how I got onto this. He has a very different approach to representation of event hierarchies. He starts off with a piece, and his basic idea is that events have functions. So what you have is a tonic region, that's what TR stands for. And then if you're going, it branches into 2 TRs. If you go to the one on the right, you get a dominant region branching off of the tonic region. Then the tonic region branches into a tonic chord, and so on. Then the dominant region branches into a subdominant region and a dominant chord, and so forth. And these are all abstract structures rather than events. Eventually, the event is spelled out at the leaf of the tree. So that's essentially the way his model works. These are the features of his model. First, he's assuming, or taking as a starting point, Hugo Riemann's tripartite categorization of harmonic functions, a TS and D for tonic, dominant, and subdominant, and variants thereof. But his innovation, which is a good one, is to treat it hierarchically. Basically, his trees look a lot like syntactic trees from the 1960s in generative linguistics, where the grammatical categories at the tree nodes are at the tree nodes, so we have tonic region and so forth, just as you would have noun or verb or adjective at a tree node in a linguistic syntactic analysis. And then realization of an event occurs only at the leaf of the tree. There's a pre-assignment of key. There's no analysis of non-harmonic tones. There's no quantification of tree relationships, anything like a distance metric. And there's no rhythmic analysis. I'm not quite sure how much the model is implemented computationally. It wasn't clear to me from his article. Here's the GTTM TPS style analysis of the same passage. Here, the rhythmic analysis shows the metrical grid and the time span segmentation, which comes from other components from GTTM. And then the events underneath is the time span reduction, where events are evaluated within this time span structure. And then that, through something called the interaction principle, helps construct the pattern of tension and relaxation. Of course, this I'm giving just a very short fragment here. But what it shows in the prolongational analysis at the top in the tree is that there's a departure and then a return to G major chord. The Tonic is achieved by the pitch by the shortest path. The G major chord is the first chord, and the shortest distance of a chord to it is to itself. So that in this case, it's a trivial resolution. And there's no other evidence to contradict that. And then the numbers in the tree indicate pitch space distances, therefore the degree of tension involved. Functions are read off the tree through a method of basically saying that function is a artifact of prolongational context. So the features of the GTTM TPS model are basically that the branching nodes are not syntactic categories. And in fact, I would argue that music does not have syntactic categories. It's one of the great differences between music and language. Branchings simply represent elaboration to the right or left. I've even gotten rid of the different node types that were in GTTM because those distinctions are represented elsewhere in the theory now. So right branching signifies a tensing motion in relation to the previous superordinate event. Left branching signifies a relaxing motion in relation to a projected future superordinate event. And that's it. Distances or degrees of tension between events are quantified in the theory. It's a quantified theory now, at least in those important respects. Keys established by the principle of the shortest path. Non-harmonic tones are represented. Rhythmic structures assigned. You can't derive the analysis without the rhythmic structure, in fact. Function is not mixed up with chord identity, as it often is in function theories. Rather, it's something different. It's not a fundamental concept, but an attribute of hierarchical context. And finally, the model is partly but not fully implemented. So I realize I'm over time, so I will stop with that. Thank you.